I was thinking, you know, maybe chapter 17 doesn't make sense to people. So what I decided to do is figure out, okay, what types of questions are given in this chapter. I think there are 5 types of questions. So I'm going to put them A through E. I want to go through and summarize. And then if you're in my class, I'm going to show you the questions I've already solved and show you which kind of question it is. Does that make sense? Because sometimes your head gets a little bit mushy when you're going through this chapter and you don't remember what comes from where and life goes crazy, okay? Then you freak out, whatever happens in your life. All right. So, for the first one, a simple ice table in Ksp. What you're basically given, you have there's either Ksp or molar solubility, one of the two, and you're solving for the other one, okay? So you're going to use an ice table, and you're going to see one ionic compound in the question. That's it. One ionic compound. That's a key there. When you see more than one, it's a different kind of problem. One ionic compound, basically going to use the ice table. In my class, or even if you haven't had my class, here's a classic example right here on the top. The molar solubility of a silver chromate. One thing, and I have the molar solubility, I want you to find K. Straight up ice table. Just write the reaction, do the ice table, that's it. Okay? In my class, you could just look up how I solved it if you want, but it's part A. Okay, let's look at part B now. Common ion. Slight variant on A. So you're given one ionic compound in another. So technically there's two ionic compounds. One's going to be soluble and one's going to be insoluble. Typically the first one is the insoluble one and the second one listed is the aqueous one. So you're going to see that's this kind of problem because the ion, usually the anion, matches in both compounds. So it'd be both of them have F- in it, or both of them have nitrate. They're both the same anion. That's how you know it's a common ion. And then you're going to use the second molarity, that's the one of the aqueous one, in the I line of the ice table. Okay, so the ice table I line for part A will be both zeros, but for part B there will be one non-zero number in the I line. A classic one that I did for that one. Let's see, let me find one that I think I did in class would be this. This is classic right here. Calculate the solubility, that's the same as molar solubility, same thing, of calcium fluoride in sodium fluoride. Okay, 2 of them, they both have fluoride. It is a common ion. So that the one molarity that you're given, the only one, is going to go in for the anion in the I line of the ice table. Okay? So that's how you know it's this type. Alright, let's look at part C now. Precipitation. There's 2 subcategories in precipitation. The first one is a will it precipitate. The nice thing about precipitation, no ice table in part C, in category C here. Don't use an ice table or you are definitely doing something wrong. Okay, so will it precipitate? That's asking will there be a precipitation or will it be aqueous? That kind of question. So you're given one ionic compound. Okay, one ionic compound. Though sometimes it could be 2 things mixed together, but you're forming one. The one way you can tell that is we'll give you 1 Ksp. So if you're mixing 2 things together, you'll see 1 Ksp value. What you're going to do is find the initial concentrations for both ions and then use Q. A classic one that I did in class while you're copying that down. Here we go. Here's a classic one. The cerium one, if you remember that from class. I asked will it precipitate? And I'm mixing 2 things. Even though there's 2 things, I care about the cerium in the first and the iodate in the second. So it's really one compound. See, there's only 1 Ksp here. So you're going to use Q. No ice table. Find Q, compare to K. That's it. All right, let's go to the next one. I guess I'll do this so you can kind of see both here. Okay, see part 2, fractional precipitation, which somebody asked me about. It's really easy to notice this one because there are multiple ions in play. Multiple ions in play. Let me see if I'll find one here. Here's one. So what you're going to do is not use Q, but use Ksp for every single ion given. Every single ion you're going to do Ksp, and you're typically asked which one precipitates first. There could be other questions, but that's a pretty typical one. And it's found by the term, whichever one gives you the smallest answer is the one that precipitates first. So the smallest answer is pretty much the answer to C2. Here's a classic one I did in class. Let me move that out of the way now. You don't have to write this down. I just want to use something to illustrate. So here we have copper and lead. So once you see copper, oops, got cut off at the top there. Once you see copper and lead, there's more than one cation in this case. It's definitely one of these. Notice that we're adding an anion, the iodine. So that's the clue. You've got multiple, say, cations and you're adding an anion, or vice versa could be true. You have multiple anions and you're adding one cation. So, and it'll be asked like which one precipitates first, stuff like that. Okay. This one you use K for each one to solve. I think I mentioned that. All right, part D, the 4th category really, is a simple KF problem. Yeah? Yeah, we kind of have to solve the problem for me to really clarify that one, but basically you're going to use a Ksp for copper iodide and lead 2 iodide in this. So there's 2 Ksps. Notice multiple Ksps are given. That's another hint, it's this kind of problem. You're going to plug it into the Ksp expression. Notice you know K for both, and then you know the copper concentration and the lead concentration. The unknown is the random other ion that you're adding. In this case, it's the iodide ion. The one that gives you the smaller concentration for iodide ion is the answer. Okay. I know it's all abstract and I'm not writing stuff down. I just want to do an overview for everybody. Later, if you have questions from a practice or something, we can do those. Okay, D. This one is a simple KF problem, kind of analogous to part A, but for KF. So basically you're going to see one complex ion and a KF value given. As soon as I find one, I'll show you what one looks like. Again, this is one I did in class as well. Right there at the top. You've got a copper concentration, ammonia concentration. You see a KF and you see a complex ion. The copper with the 4 ammonias on it. So it's one of these. You're just straight up ice table. Now this has, this is a combination problem because there's also a dilution. I'm going to mention that in a moment. But this also involves a dilution. Similar to what we saw for C part 1. But I could have even simpler question than this one with where I'm not mixing stuff together. Okay, got to use the ice table to solve that one. The last one, E, usually people get mixed up on C2 even though the math is super easy, but really I would say the hardest one is part E. It doesn't really have a classic name, but I call it a mixed K question. What you're given is an ionic compound, pretty much always, in all the questions that I've ever seen. And you're given, ionic compound and another compound. But you're going to notice those 2 compounds don't share an ion. So it's not B, the common ion type. This is 2 compounds totally different. Okay. The second compound could either be acidic, and so it has some Ka or Kb attached to it, or it could be a complex ion, so it has a Kf associated with it. So there's more than one K in place, more than one compound in place. To solve this, you have to write an overall reaction for both, combine these 2, the Ksp and say a Kf together. You have to figure out what the total K is, and then use an ice table. One that I did in class is this one, part B of this one from class. Notice I have AgBr, there's my first compound. It's an ionic compound, Ksp kind of compound. And then I add thiosulfate. That's not common. That's not, basically, that's not in silver bromide. So it's a second type of ion. And notice that Kf is given, so this is a classic part E. Yes?
When it's asking the free concentration of something, is that asking for the E line of the ice table?
Right. When you see something like, what's the free concentration, that just means that ion by itself, and that number comes from the E line of the ice table. So free just means by itself. Okay, there's one more page, joy, I know. Okay, so those are the 5 parts. I just have special notes here. Sorry, this is not in my reader because I just thought of it last week, so I just made it up. Okay? Special notes, or other tools, I guess. 3 things. Some problems involve stoichiometry. That means when there's not a 0 on the unfavored side. You need a 0 on the unfavored side. My class, that's how I explain it. I don't know how your other instructors explain that. That's part A, B, D, and E. Could have stoichiometry, but doesn't have to. So if you're doing many of these, you want to check to make sure there's a 0 on the unfavored side. Okay. Some of these problems, A, B, C, or E, could ask about a percent unprecipitated. That is, I thought about it a little bit, that's really similar, if you remember acid-base stuff, to percent ionization. It's pretty much the same thing. It's 100 times the equilibrium concentration in the numerator divided by the initial. So it's basically the value from the E line up here divided by the value from the I line of the ice table, typically. Okay, so sometimes a percent unprecipitated can be stuck into a problem. Sometimes stoichiometry can be stuck into a problem. Sometimes dilution can be stuck into a problem. How do you know if there's dilution in it? If it ever says that 2 things are being mixed and both have a volume and a molarity, then you have to use the dilution formula. This typically happens on C and D of the 5 that I went through. Now the last sentence, this is it, I promise. The good news is any of these things that we've discussed so far can be combined into one question. Now on a final, what we would do, just to make it gradable really, is we have to separate each part out. So what I would do is think about these 5 categories and think, okay, just use the little tools, what's given basically, what's given to recognize it, and just use that particular solving technique. Then we go to the next part of that question, reevaluate. What kind of question is this one? And use the appropriate technique to solve that one. So I consider each part of a long answer problem as separate questions. Okay? All right. I suppose you want me to do an example. Yeah? Okay. I had a couple to choose from. This one you probably have kind of seen before, but this is a really good one. Right here. Now this I wrote in 1 sentence or 2 sentences, but this is actually a 1, 2, 3, 4, 5 part problem. So on a final, this would be written in 5 parts. But here, because I didn't have to do that, I didn't do that. And that would be a lot of writing. Okay, so. Again, on a final, so I'll write out how it would be on a final. Part, kind of, if you want, part A. Is this going to confuse you if I say part A? I don't mean from what I just showed you. I'm just the first thing I would do. Okay. Notice that things are mixed. So I must do what kind of problem? Dilution. So on a final, it would say, what are the initial concentrations after being mixed? So what you would do is say, okay, well, the 2 important compounds are chromate and silver. Why do I ignore potassium? Spectator iron. Why do I ignore nitrate? Spectator, yeah. Let me ask this. Well, people from other classes, do you know why these are spectator ions? They're conjugates of a strong. So they come from, this is a conjugate of nitric acid, this is a conjugate of potassium hydroxide. So they're called spectator ions. Unfortunate if you haven't learned that in another class, but if you know what the strong acids and bases are, all the conjugates are neutral. So we ignore them. Gone, garbage. Okay, so I only care about the concentration of the chromate. Initially, I'll put a 0 for the initial, and the concentration of the silver initially. Let's calculate those. For the chromate, that's, I need the molarities, initial molarity and volume divided by the final volume. That's just using the dilution formula to get the final molarity. I started with 0.35, and I started with 200 milliliters. I end with, what number goes on the bottom? 400 total volume. And this turns out to be 0.175 molar. Same calculation for the second one, except I use its molarity, 0.01, times 200 initially, divided by 400. This turns out to be 0.005. I'm not going to add other digits for now. So that would be kind of part A. Those are the initial concentrations. Part B, if I was going to separate this out into parts, would ask you, does Ag2CrO4 precipitate? What technique will I use to solve this? Ice table, yes or no? No. What will it be? Q. Will it precipitate? There's one compound. I have the initial concentrations. I'm going to stick it in Q. So let's try that. Q is equal to silver initial squared CrO4 2 minus. Is it too crazy that I put a squared by the silver? Is that okay? Or should I explain that more? You have to raise your hand.
What does the 0 mean?
The 0 means initial. So that's back from chapter 14. Subscripted 0 means the initial. When you enter the problem or the I line of the ice table. Okay. So, this is 0.005 times 0.01. That's squared. And this turns out to be 4.4 times 10 to the minus 6. I compare that to K, which has to be given on a final. 1.1 times 10 to the minus 12. Okay, does it precipitate? Yes, because Q is greater than K. Okay, that would be kind of like part B of this question. Okay, part C of this question. Any questions so far? Part C would ask, what's the free silver ion concentration at equilibrium? There's the free for you. This means the E line. So, what technique will I use here? Ice table, because I want an equilibrium concentration. This so far, just part C alone, is your simple Ksp question. The first one I went over of the 5. Okay, so let's try that. You would write the reaction out. There's my reaction. Yeah. Now, you're going to write the numbers in. 0.005, this is from before, and 0.175. What do I do now? Oh, that's a good comment. Let me ask everybody, do I need to multiply this by 2?
No.
I don't. I would only do that on the C line, but never on the I line. The I line goes in as is. What do I do now? Do I go to the C line? I cannot because I don't have a 0 on the unfavored side. So now, surprise, I didn't expect it, but there's a stoichiometry problem. Now, do other people from other classes know what the heck I'm talking about now? What about the 0 on the unfavored side? Okay. No-ish? Oh wait, tell me if I need to explain it. Okay. That's what I wanted to know. Alright. This happened when you did the buffer problems back in chapter 16. Whether or not your instructor explained this, you were doing stoichiometry problems, usually before doing the ice table. I don't know if you remember that. And when you did titrations, you do stoichiometry before doing the solving part. Here's the general rule that works in all scenarios. You look at K, it's right there, and you figure out which side is favored, right or left. And everybody? Yeah, K is small, so the left side is favored. That means the right side is unfavored. Got that? People in other classes? Good? Okay. See how there's no 0 in the I line on the unfavored side, which is the right-hand side over here? No 0? You cannot start an ice table if that's true. You cannot start an ice table unless there's a 0 on that unfavored side. That was true all through chapter 16 and beyond. Sometimes instructors don't clarify that. Well, maybe I should ask, do other instructors teach that? How do you know to do that? Okay, whatever, it's cool. Doesn't matter. Okay, so you cannot start an ice table, you have to do stoichiometry. You pick the smaller number, which is this one. Now here's, you had said the 2. Here's where a 2 would go in stoichiometry. So I have a 2 there, and I need to subtract this whole number here. So what am I going to put in the middle? Yeah, half of this number, 0.0025, and minus 0.0025. So you're basically shifting it over to make a 0 somewhere. Unfortunately, because there was a 2 by the silver, and that was a smaller number, I have to put a 2 whenever I'm subtracting or adding in stoichiometry to account for the molar ratios. Turns out to be 0. This is what I wanted right there. And this is 0.173. This is now the I line. I can have an I line because I have the 0 on the unfavored side. Okay. Trust me, you need this for the final. Okay, C. Yes? Why did this? Why does this look so weird? Okay. Normally I would just subtract 0.005 because I want the smallest number to go down to 0. It's the limiting reactant. However, because of that 2 there, I need to have a 2 because this is a stoichiometry problem now before the ice table. So 2 times what equals this number is basically what I'm asking myself. And so I need that number here though. So I have to find out what that is to put it here. Normally when you've done titrations, typically there's no 2 here, so you just subtract this number from both sides. But it does occasionally happen like this. Yeah? Yeah, you could have subtracted 0.005 on the left, on the silver, and then go minus half of 0.005 on the right. That's the exact same thing. That's totally fine if you like that method. Okay, C line plus 2x. Here you asked me earlier where the 2 goes. Right here and right there is stoichiometry. There's a total of 3 places that it goes. The 2 goes here and there. You'll see one more place in a second. Plus x. E line, 2x, and 0.173 plus x. So I've been doing the ice table, so I do my typical solving Ksp, 1.1 times 10 to the minus 12 equals 2x. Here's the 3rd place that 2 goes, squared. And then 0.173 plus x. I know, I apologize that your brain is exploding right now. I just decided you'd probably rather see a harder problem than an easier problem, so I picked a hard one. Okay, but it's also final worthy. So, okay, what am I going to do next? Drop the x. Assume it's 0 compared to the other number next to it. So if I solve for x, that's going to equal, in this case, 1.3 times 10 to the minus 6. Just kind of dividing through, taking the square root. All right. Is that the copper concentration that I was looking for? No, what is the copper concentration I was looking for? Yeah, you just look at the E line of the ice table. It's 2x. It's the free silver concentration. So the concentration of silver is equal to 2x. I get that from the E line. And that's equal to, I got that somewhere, oh, just 2 times this. 2.6 times 10 to the minus 6 molar. There's the answer to that part, which I'm calling part C. The last part, I'll call it D, is the percent unprecipitated of silver. I guess I don't need the brackets on there, but yeah. Percent unprecipitated of silver. So, remember, this is just like percent ionization. Percent unprecipitated is equal to 100 times the initial concentration in the denominator. What would be that number? 0.005 if you look backwards a little bit. What would be this number in the numerator? Yeah, the 2x, that number right there. 2.6 times 10 to the minus 6. Those are both in molarities, that'll cancel out, and I get 0.052, which means very little of it is unprecipitated. 0.5%, or less than that. Whatever, a small number. I'll give you a moment to process before we go on. See if you have a question. So this is one of those combo deals. Okay. All right. Take care, everybody. I'm still going though. Okay, two questions. Let me do yours first, and then we'll go on to titrations and so on. Yours was if there was no, not that one. Whoa, is everybody okay? Sorry, I offended. I blew it, apparently. That was another review. Okay, thank you for pitying me and saying that you have another review. I don't believe you at all. Okay. All right. If there was a 3 here, where'd you go? Is that your question? Then the C line would be 3x. And then the answer would be 3x. Up here would be 3 times 1/3 of this number. Because you want this to be 0. And then 1/3 of that number would be right there. Okay. All right. Did I answer your question already? What was your? Then I'll go to yours. Sorry, it was first. Yes. Huh? The assumption. How do I know to make this assumption? When k is small compared to the other number, it's going to work. Yes.
So for part D, that is the percent unprecipitate, or is that the percent that is precipitated?
This is the percent unprecipitated. That means that very little of the silver is left, so it's an unprecipitated amount. The amount precipitated would be 100 minus this number, or 99.948.